In this lecture, we will discuss a few of the many applications of Dirac Delta function that was introduced in the previous video. I underscored the fact that the Dirac Delta function is defined for continuous variables, and it was introduced by Dirac, an English theoretical physicist, a 1933 Nobel laureate, and a man who did wonders by creating or proposing the spectacular tool called Dirac Delta function, which has so many important applications. We made a mention of some of the many applications of Dirac Delta function, and in this video we shall highlight two important areas in which use of Dirac Delta function can pull us out of danger, can rescue us from falling into the trap of infinity that I mentioned in the previous video. Let us recapitulate, let us quote the essential results that we arrived at previously involving the Dirac Delta function. The one-dimensional Dirac Delta function is written as shown, putting x within the first bracket and placing it to the right of the delta symbol. And this is the Dirac Delta of x around x equal to 0. Let us graphically represent it, and this is how it is done. You see in the right an infinite spike at x equal to 0, implying that the width or spread along x is 0. We derived it starting from a rectangle or a box that enclosed unit area, and we saw how the rectangle turns into a Dirac delta if we reduce its width indefinitely but carefully and steadfastly hold on to its area magnitude, which was set at unity. So this is the graphical representation of the Dirac Delta function around x equal to 0. The mathematical representation of the Dirac Delta function has been shown. Dirac Delta of x is 0 for x not equal to 0 and infinity at x equal to 0. And the 0 width and infinite height are coordinated in such a way that the area under the curve is unity. We also discussed the dimension of the Dirac Delta function. We proved that the dimension of Dirac Delta of x is inverse of the argument x, and this you can see represented in the blue box. We also derived some other delta functions. For instance, Dirac delta of x minus a. It is an infinite spike at x equal to a, as you can see in the figure. It is obtained from Dirac delta of x simply by replacing x by x minus a. You can compare the respective graphical plots, as well as the corresponding mathematical relations which have been written side by side, that is, in parallel, for easy comparison. So this is the Dirac Delta function of x minus a, or the Dirac Delta function around x equal to a. The graphical plot along with its mathematical representation being shown explicitly. In a similar manner, we get the Dirac delta of x plus a with a replacement of x by x plus a. The graphical plot and the mathematical relations have been shown over there. It is the Dirac delta function around x equal to minus a as indicated by the infinite spike at x equal to minus a. And let us emphasize that these are one-dimensional Dirac delta functions derived and discussed previously. We now move further to recapitulate the results we got for three-dimensional situation. The three-dimensional Dirac Delta function, delta of vector r, can similarly be obtained by replacing x by vector r, and have a look at it. Unlike the previous one-dimensional cases where integration was over x-axis, here the integration is over all space. And replacing x by vector r minus vector r0, we can define and arrive at the Dirac delta function of vector r minus vector r0 as written neatly in the slide. So this was how we introduced Dirac delta function, derived it from rectangle function, represented it graphically, wrote down its mathematical expression, and finally discussed what its dimension was. Keeping all these in mind, let us move ahead to study some of its applications. Let us now study one application of Dirac delta function. It was previously mentioned that with the help of Dirac delta function, we can easily express the mass density of a discrete distribution of masses. To start with, let us consider a point mass, and we shall write down the mass density of a point mass. Look at the right slide and consider mass density of a point mass, an isolated lump or aggregation or concentration of matter. Let us proceed by answering a question. A mass m is located at a point on the x-axis, so we are discussing a one-dimensional case. And our task is to find the mass density of this discrete presence of a mass. Let us come to the answer. Let us label the point where the mass is sitting as x equal to 0. Mass being on a line which we take to be the x-axis, let us think of a quantity which is mass divided by the length that the mass occupies, that is, the linear spread or extent of mass, and define it as the linear mass density lambda. So, if an elemental length dx houses or carries dm amount of mass, then the linear density of mass would be dm by dx. Since mass may vary from point to point on x-axis, we see that lambda is a function of x, so we write lambda of x. If we try to find the linear mass density lambda of the mass at x equal to 0, we run into grave problem as seen from the attempt that we have made in the slide. Since the point mass m is situated at a point and occupies no length, lambda is m by 0, and that means we get infinity. In fact, a finite mass confined to 0 length would gift us an unmanageable infinity. And as mentioned in the previous video, physicists are afraid of infinity. We cannot lock horns with it, but we are not doomed. And it is not the end of us. We have a way, because we are armed with Dirac delta function, with which we can circumvent the infinity and brush aside the ugly and angry stare of infinity. The rule is, whenever we find ourselves beset with problems, any type of problems whatsoever, what we do is we keep our heads cool and take a re-look at our strength. And here too, we would do that. Let us check what finite numbers are there to deal with, and it is obviously the mass m, because though it occupies 0 space and gives infinite mass density, the total mass is finite. from the relation lambda equal to dm by dx, let us write dm as dm equal to lambda dx, and herefrom the expression of the total mass m follows in terms of the linear mass density lambda of x as we integrate over the entire x-axis, namely from minus infinity to plus infinity. Let us thus collect all the information or data that we have been able to collect, and it is summarized in the green box. Lambda is infinity for x equal to 0. Lambda is 0 at all other points, that is at x not equal to 0, where there is no mass. And the total mass is m, the relation being expressed as an integral in terms of the linear mass density. Let us take a closer and a more careful look at the green box. It does remind us of the mathematical representation of Dirac Delta function. Let us write the essential relations in the same slide for easy comparison, and the integral portions of the two relations catch our attention because they are of similar structure. Let us consider the integral involving lambda of x dx as integrand, the right hand side of which is m, that is m into unity, and instead of unity we can plug in the expression of unit area under the Dirac Delta curve. This is shown in the box with black border. Let us thus compare the two integrals, the left one carrying the linear mass density lambda of x as the integrand, while the right integral has m into the Dirac Delta function as its integrand. This gives the expression of the linear mass density, which is mass m times the Dirac Delta function of x. So we have solved the problem. The linear mass density of a discrete point mass will be the mass times the Dirac Delta of x minus its x position, which is 0 for the mass considered. Finally, let us check whether our result is correct. Integrate over the entire x-axis with lambda x dx as the integrand. Put the value of lambda, that is m into Dirac Delta of x, and integration yields the total mass m, where we have used the fact that area under the Dirac Delta is unity. So our result is correct. We have quoted the essential result, namely the expression of the linear mass density of a point mass m located at a point whose x-coordinate is taken to be x equal to 0, and it is m times the Dirac Delta of x minus the position coordinate, which is 0. In problem solving, we shall employ this formula. Let us consider the question now. Consider the given linear mass distribution. We see that capital M1 sits at x equal to minus 1, small m is at the origin x equal to 0, and capital M2 is at x equal to 4. Let us come to the question now. We have to find the mass density of this linear distribution of masses. What will the answer be? The mass density of capital M1 sitting at x equal to minus 1 is, according to the prescription, capital M1 into Dirac Delta of x minus of minus 1, since minus 1 is its x coordinate, and so we get M1 into Dirac Delta of x plus 1. The mass density of small m sitting at x equal to 0 is small m into Dirac Delta of x minus 0, that is small m into Dirac Delta of x. The mass density of the mass capital M2 located at x equal to 4 is, as per prescription, capital M2 into Dirac delta of x minus 4. So the mass density of the linear distribution of mass is the sum of the mass densities of the individual masses, capital M1, small m, and capital M2. This is furnished in the blue box at the bottom. Let us find the total mass that is given by the formula, namely integration over lambda of x into dx, the integration being from minus infinity to plus infinity. Let us put the value of lambda of x, and let us recall that the integrations over Dirac delta are unity, since the points x equal to minus 1 in the first integral, x equal to 0 in the second integral, and x equal to 4 in the third integral are all included in the range of integration. In fact, you have to perform integration over the entire x-axis. So with this, we get the total mass of the linear mass distribution. We have thus also verified that result of linear mass density lambda of x is correct. Having discussed the application of Dirac delta function in finding out the linear mass density for a discrete linear mass distribution, let us consider a discrete surface distribution of mass, that is, masses on a surface sitting here and there, not continuously distributed but scattered. We wish to find the mass density. Let us address the case through answering a question which is as follows. Given that masses capital M and small m0, m1, m2, m3 and m4 are located at certain points on a surface, which is the xy plane, say, and the coordinates have been shown, we are to find the surface mass density for this discrete mass distribution. Let us find the answer to the problem. Let us define surface mass density as sigma, which is mass divided by the area it occupies. So, if an elemental mass dm occupies a region of surface area dA, then the surface density is, by definition, dm by dA. This we denote by sigma, which is a function of the coordinate vector r of the mass or the masses under consideration. And since vector r for a point on the xy plane corresponds to two coordinates x and y, we can alternately designate sigma to be a function of x and y as shown. We note that the mass distribution is a discrete distribution, and so we need the help of Dirac delta function to write down the mass densities that we do now. Mass capital M is at origin, and let us write the mass density. Since it is a two-dimensional case, we will have product of two Dirac deltas, and so the surface mass density will be capital M into Dirac delta of x minus its x position, which is 0, multiplied by another Dirac delta of y minus its y coordinate, which is also 0. So what we get is capital M into Dirac delta of x multiplied by Dirac delta of y. Then we come to the mass m0 located at x equal to a, y equal to b, and so the argument of the two Dirac deltas will be x minus a and y minus b respectively, as you can see in the right column. The mass m1 at x equal to minus a and y equal to 0 corresponds to a mass density of m1 into Dirac delta of x minus a multiplied by Dirac delta of y minus 0. That is, it turns out to be m1 into Dirac delta of x plus a into Dirac delta of y. And similarly, we get the mass densities of the remaining masses as shown in the slide. You can see the calculations for M3 as well as for M4. The mass densities have been written. We now add the individual mass densities to get the result, and here it is. Let us check our result by evaluating the total mass using the formula, namely integration over sigma dx dy as shown. We can evaluate using the property of Dirac delta function that area under it is unity. So the total mass has been obtained. You can check the calculation, which is easy and done here. It follows that our calculation in evaluating the surface mass density of the discrete mass distribution was right, and for this reason we could achieve the correct result due to proper use of the Dirac delta function. Let us extend the problem further of finding the mass densities of discrete mass distribution. And now we consider two masses. One is small m and another is capital M, resting at 2 points in a 3D space. So this is the question. Let us take mass small m to be at the origin and the mass capital M to be at a point whose coordinates are given in the question. We are to determine the volume density of mass. First, let us designate the symbol rho to represent the volume density of mass and define it to be the mass divided by the volume which the mass occupies. Also, being a 3D problem now, the position vector would involve three components, that is, three coordinates: x coordinate, y coordinate, and the z coordinate. Since mass may be different at different points, that is, mass is a function of position, we have written rho as a function of vector r, or in other words, rho is a function of x, y, and z. The mass density of M at the origin, defined as x equal to 0, y equal to 0, z is equal to 0, can now be written, and it would involve the product of three Dirac delta functions. It is small m into Dirac delta of x minus 0 multiplied by a second Dirac delta of y minus 0 multiplied by a third Dirac delta of z minus 0. And similarly, the mass density of the mass capital M is capital M into the product of three Dirac deltas. One is Dirac delta of x minus 3, since capital M sits at x equal to 3, and then comes the Dirac delta y minus 4, since capital M has y coordinate 4, and finally comes the Dirac delta z plus 5, since the mass capital M has z coordinate z is equal to minus 5. Clearly, we are in a position to write down the mass density of the given distribution, and it has been shown. The mass density rho is the sum of the individual mass densities, and it is written in the box with a brown outline. Can we put our faith on this result? Let us verify our result by finding the total mass. The formula for total mass is integration over rho vector r d of vector r, and we have to integrate over all space. We put the rho we got in the integrand an integrate, which essentially turns into integration of the Dirac deltas, and in each case we get unity, since area under Dirac delta curve or plot is unity. So the result is small m plus capital M, representing the total mass of the considered distribution. We now consider another application of the Dirac delta function, and this is writing down the charge density of a discrete charge distribution. Let us solve certain problems in this regard. The first problem. You can see a point charge minus q located at some point in 3D space, and we have to find its charge density. Let us for simplicity choose the origin of the coordinate system at the location of minus q. So we have x, y and z axis merging at 0, 0, 0 where minus q is located. Let us define the volume charge density rho of vector r as the total charge divided by the volume that the charge occupies. And the charge is minus q while the volume occupied is 0, since the charge is attached to a point and a point has 0 volume, no length, no breadth, no height. Clearly, therefore, the volume charge density that we arrive at is infinity, and we seem to be in trouble. But keeping our heads cool, let us accept it and at the same time write down all the properties or features of the discrete charge distribution we have got. And you can see the properties housed in the green box. At vector r equal to 0, rho is infinity. At vector r not equal to 0, rho is 0, since charge is only at the origin and nowhere else. Also, the total charge is minus q, and let us write it mathematically. The integration over all space of rho d tau has to be the total charge, and it is minus q. Here d tau represents an infinitesimal volume element, rho being the volume charge density. Let us compare the results of the charge density rho with the three-dimensional Dirac delta function shown in the blue box. Our aim is to derive the charge density of the discrete charge, namely the point charge minus q at the origin. Let us focus attention to the two integrals indicated by means of the red ticks. Let us consider the integral involving rho d tau, which is minus q and shown in the box with green outline. Let us write the right hand side, that is minus q, as minus q into the numeric 1. And for the numeric 1, let us substitute the property of unit area under Dirac delta as shown in the box with white outline. Comparison gives the volume charge density rho, which is a function of vector r, as minus q into Dirac delta vector r. Let me remind that this is the expression of the volume density of charge for a charge located at the origin. If instead of minus q, a positive charge, say q, is at the origin, then the volume charge density would be, drop the minus sign and write q into Dirac delta vector r. We would do some more problems. We would find charge densities in some more discrete charge distributions as follows. We would take up some standard discrete orientations or charge distributions. Let us first discuss some monopole distributions. We will consider one charge q or minus q and attach coordinates to it in various ways and write down the charge density. First, a monopole Q or minus Q located at some point in space. Consider the first problem of the monopole Q at a point, say vector r0, that is the x coordinate is x0, y coordinate is y0, and the z coordinate is z0. The charge density is thus Q multiplied by Dirac delta vector r minus vector r0. We can also write it in component form as Q into Dirac delta of x minus x0 into Dirac delta of y minus y0 multiplied by Dirac delta of z minus z0. And we check whether this charge density gives us or generates the total charge Q, and indeed it does. And similarly, we have for the other problem of minus Q at vector r0, the charge density to be as shown, the difference being that now we have minus Q instead of Q. Let us recast the same problem by supposing that the monopole Q is placed on the x-axis at x0, and so the Dirac delta part containing x would be x minus x0 since the x coordinate of the charge is x0. The Dirac delta part containing y would be y minus 0 since the y coordinate of Q is 0. That is, it would simply be Dirac delta of y. Similarly, the z part would be the Dirac delta of z, the z coordinate of Q being 0. So volume charge density rho is obtained, as you can see within the green outlined box. We check if we get back to the total charge from this rho, and indeed we succeed in getting the total charge back. If the discrete point charge Q is taken to be at minus x0, that is on the negative x-axis, we proceed similarly. As you can see, check the results. If minus Q is at positive x-axis, we have what is shown in the green box. And if minus Q is at minus x0, that is on the negative x-axis, we have a charge density written within the blue box. I wish you verify the results and satisfy yourselves. Let me tell you one thing. To achieve mastery over anything, you have to play with it, juggle with it. So let us now put the charge at various positions on y-axis and write down the charge densities and also find the total charge. In this slide, we see that Q is located at y0 on the y-axis, and then we have minus Q on y-axis at y0. The slide shows the monopole Q at minus y0. Check the charge density and the total charge. And now minus Q at minus y0, that is on the negative y-axis. The same is done by placing a monopole at various positions on the z-axis. You are expected to pause the video, write the answers on your own, and then verify through a comparison with your answer and what is written on this slide. Spot the mistake, if any, and correct it accordingly. Here you find charge Q at Z0 on the positive z-axis, and then minus Q located at Z0, and then Q at minus Z0, and finally minus Q at minus Z0. Let us solve a similar problem where we are asked to find the charge density of a 4 coulomb charge sitting at x equal to 4, y equal to minus 5, z is equal to minus 1. The volume charge density would be rho, which is 4 coulomb multiplied by 3 Dirac deltas, namely Dirac delta of x minus 4 into Dirac delta of y plus 5 into Dirac delta of z plus 1. And the total charge indeed turns out to be 4 Coulomb, signaling the fact that we wrote the charge density correctly. We discussed how to find the charge density of a monopole, whatever be its coordinates, with the help of Dirac delta function. Let us proceed to do some more problems. We would find charge densities in case of some more discrete charge distributions. For instance, a dipole, a quadrupole, linear or planar, an octupole, etc. Let us now find the volume charge density of a discrete distribution of two charges. One is minus q at z1 and the other is q located at minus z2. That is, charges are on the z-axis. The volume charge density ρ is written. Since the charge lies on the z-axis, the x and y components of the Dirac deltas would be same, namely Dirac delta x into Dirac delta y, and this is underlined in the blue. The z part would differ. We can find, as in the previous problems, the total charge, which is 0, since area under Dirac delta curve is unity. Now let us sail over to the next problem, where we consider a dipole. The charges are placed along the z-axis as in the previous problem. It is given that q charge sits at z and minus q sits at minus z. Now we have to be a bit careful in writing the charge density. The x and y parts are same as in the previous problem, and this is underlined in the blue. Only the z part will vary. Note that in this problem, the charges are positioned at z and minus z. This means that the variable along z-axis cannot be written as z. So let us write the variable as z prime along z-axis. We thus have constructed the volume charge density that you can see in the slide. With this charge density, we have evaluated the total charge, and it turns out to be q minus q, that is 0. We next consider a linear quadrupole with the central charge being minus 2q. The terminal charges are q and q at a distance a from the central charge, and they are placed on either side of the central charge and on the same line. The charge density can be similarly found out. The first step is to attach the coordinates as shown. We take the central charge minus 2q as the origin, and we write down the charge density. Since charges are situated on the z-axis, the x and y part will be same, that is Dirac delta of x into Dirac delta of y, and this is underlined in the blue. The z part will vary only, it being Dirac delta of z for charge minus 2q situated at z is equal to 0, and Dirac delta of z minus of minus a, that is z plus a, for the charge q located at z is equal to minus a. And finally we have for the charge q at z is equal to a, Dirac delta z minus a, as you can see in the last term. Now we can verify the expression for charge density through a calculation of the total charge. It is there for you to check. We now take up a similar problem, namely writing down the charge density of a linear quadrupole, and the difference you see from the previous arrangement is in the sign of the charges. So you can attach the coordinates and then write down the charge density as in the previous problem and find the total charge for verification of the result. We next consider a planar quadrupole. We have to find the volume charge density. Let us attach the coordinates assuming origin at one corner. We note that the plane is the xy plane as the z coordinate of the charges is z is equal to 0. So the Dirac delta part involving z would obviously be Dirac delta of z minus 0, that is Dirac delta of z, as shown with a blue underline. You can evaluate the total charge and check. In a similar manner, we can write down the expression of the volume charge density of the octupole shown in the figure. In fact, we have drawn a cubical box of size A carrying a charge of magnitude Q, alternately repeating in sign. Write down the charge density and verify the result written in the slide, and also calculate the total charge. The penultimate problem. Consider two charges Q1 and Q2 sitting at vector R1 and vector R2. We have to write the charge density, and it is Q1 into Dirac delta of vector R minus vector R1 plus Q2 into Dirac delta of vector R minus vector R2. Suppose vector R1 has coordinates x1, y1, z1 and vector R2 has coordinates x2, y2, z2. Then charge density can be written by splitting the Dirac delta into x part, y part and z part as shown in the slide. The last problem before we call it a day. It is a simple problem. We have to write down the three types of charge densities of a charge Q. First, the linear charge density is Q into Dirac delta of x, assuming that charge Q is at x equal to 0. Again, if we suppose that the charge Q is at the origin of a 2D Cartesian coordinate system, then the charge density becomes Q into Dirac delta of x into Dirac delta of y. And the expression of volume charge density involves presence of another Dirac delta, namely Dirac delta of z, as we assume that Q is at the origin of a 3D Cartesian coordinate system.